In this video, I want to give you more practical tips for getting gradient descent to work. The ideas in this video will center around the learning rate alpha. Concretely, here's the gradient descent update rule, and what I want to do in this video is tell you about what I think of as debugging and some tips for making sure that gradient descent is working correctly. And second, I want to tell you how to choose the learning rate alpha, or at least how I go about choosing it. Here's something that I often do to make sure that gradient descent is working correctly. The job of gradient descent is to find the value of theta for you that hopefully minimizes the cost function j of theta. What I often do is therefore plot the cost function j of theta as gradient descent runs. So the x-axis here is the number of iterations of gradient descent, and as gradient descent runs, you hopefully get a plot that maybe looks like this. Notice that the x-axis is number of iterations. Previously, we were looking at plots of j of theta where the x-axis, where the horizontal axis, was the parameter vector theta. But this is not what this is. Concretely, what this point is I'm going to run gradient descent for 100 iterations, and whatever value I get for theta after 100 iterations, I'm going to get some value theta after 100 iterations, and I'm going to evaluate the cost function j of theta for the value of theta I get after 100 iterations, and this vertical height is the value of j of theta for the value of theta I got after 100 iterations of gradient descent. And this point here, that corresponds to the value of j of theta for the theta that I get after I've run gradient descent for 200 iterations. So what this plot is showing the value of your cost function after each iteration of gradient descent, and if gradient descent is working properly, then j of theta should decrease after every iteration. And one useful thing that this sort of plot can tell you also is that if you look at the specific figure that I've drawn, it looks like by the time you've gotten out to maybe 300 iterations, between 300 and 400 iterations in this segment, it looks like j of theta hasn't gone down much more. So by the time you get to 400 iterations, it looks like this curve has flattened out here. And so way out here at 400 iterations, it looks like gradient descent has more or less converged because your cost function isn't going down much more. So looking at this figure can also help you judge whether or not gradient descent has converged. By the way, the number of iterations that gradient descent takes to converge for a particular application can vary a lot. So maybe for one application, gradient descent may converge after just 30 iterations. For a different application, gradient descent may take 3,000 iterations. For another algorithm, for another learning algorithm, it may take 3 million iterations. It turns out to be very difficult to tell in advance how many iterations gradient descent needs to converge, and is usually by plotting this sort of plot. Plotting the cost function as we increase the number of iterations is usually by looking at these plots that I try to tell if gradient descent has converged. It's also possible to come up with automatic convergence tests, namely to have an algorithm try to tell you if gradient descent has converged. And here's maybe a pretty typical example of an automatic convergence test. And such a test may declare convergence if your cost function j of theta decreases by less than some small value epsilon, some small value 10 to the minus 3 in one iteration. But I find that usually choosing what this threshold is pretty difficult, and so in order to check if gradient descent is converged, I actually tend to look at plots like these, like this figure on the left, rather than rely on an automatic convergence test. Looking at this sort of figure can also tell you or give you an advance warning if maybe gradient descent is not working correctly. Concretely, if you plot j of theta as a function of the number of iterations, then if you see a figure like this where j of theta is actually increasing, then that gives you a clear sign that gradient descent is not working. And a figure like this usually means that you should be using a learning rate alpha. If j of theta is actually increasing, the most common cause for that is if you're maybe trying to minimize a function that maybe looks like this, But if your learning rate is too big, then if you start off there, gradient descent may overshoot the minimum and send you there. And if the learning rate is too big, you may overshoot again and then send you there, and so on. So that, well, what you really wanted was for it to start here and for it to slowly go downhill, right? But if the learning rate is too big, then gradient descent can instead, keep on overshooting the minimum, so that you actually end up getting worse and worse, so sort of getting to higher values of the cost function j of theta, so that you end up with a plot like this. And if you see a plot like this, the fix usually is to just use a smaller value of alpha. Oh, and also, of course, make sure that your code does not have a bug in it, but usually too large a value of alpha is the most common, could be a common problem. Similarly, sometimes you may also see j of theta do something like this. It may go down for a while, then go up, then go down for a while, then go up, go down for a while, go up, and so on. And the fix for something like this is also to use a smaller value of alpha. I'm not going to prove it here, but under mild assumptions about the cost function j, which does hold true for linear regression, you can show, or mathematicians have shown, that if your learning rate alpha is small enough, then j of theta should decrease on every single iteration. So if this doesn't happen, it probably means alpha is too big and you should set it smaller. But of course, you also don't want your learning rate to be too small, because if you were to do that, then gradient descent can be slow to converge. And if alpha were too small, you might end up starting out here, say, and end up taking just minuscule baby steps, right? And just taking a lot of iterations before you finally get to the minimum. And so if alpha is too small, gradient descent can make very slow progress and be slow to converge. To summarize, if the learning rate is too small, you can have a slow convergence problem. And if the learning rate is too large, j of theta may not decrease on every iteration, and it may not even converge. In some cases, if the learning rate is too large, slow convergence is also possible. But the more common problem you see is that j of theta may not decrease on every iteration. And in order to debug all of these things, often plotting that j of theta as a function of the number of iterations can help you figure out what's going on. Concretely, what I actually do when I run gradient descent is I would try a range of values. So just try running gradient descent with a range of values for alpha, like 0.001, 0.01. So these are a factor of 10 differences. And for these different values of alpha, just plot j of theta as a function of number of iterations. And then pick the value of alpha that seems to be causing j of theta to decrease rapidly. In fact, what I do actually isn't these steps of 10. So this is a scale factor of 10 if each step up. What I actually do is try this range of values, and so on, where this is 0.01. I'll then increase the learning rate threefold to get 0.03, and then this step up, this is another roughly threefold increase from 0.03 to 0.01, and so these are roughly trying out gradient descent with each value I try being about 3x bigger than the previous value. So what I'll do is try a range of values until I've made sure that I found one value that's too small and make sure I found one value that's too large, and then I sort of try to pick the largest possible value or just something slightly smaller than the largest reasonable value that I found. And when I do that, usually this gives me a good learning rate for my problem. And if you do this too, hopefully you'll be able to choose a good learning rate for your implementation of gradient descent.